In this video, we shall look at a couple of review problems on capacitor. First, a brief introduction. Assume you have a parallel plate capacitor, like that. The potential difference between the plates is delta V. The left-hand side plate is positively charged, and the right-hand side plate is negatively charged. The total charge is, let's say, Q. So Q is proportional to delta V, and the proportionality constant is what is known as the capacitance of this capacitor. So assume that this parallel plate capacitor has the following dimensions. The area of the plates is, let's say, A, and the distance between the plates, let's call it D. Let's assume that the region between the plates is filled with a dielectric constant K. So the capacitance C can be expressed in terms of all these dimensions in a following manner. It is epsilon naught, where epsilon naught is the permittivity of vacuum, with a value of 8.85 times 10 to the power minus 12 in SI units, times the dielectric constant K, times the surface area A, over the separation distance of the plates D. And of course, the capacitance is measured in the units of farad, or abbreviation capital F. Now let's look at the problems. Problem 1. An isolated charged conducting sphere of radius 12 cm creates an electric field with a magnitude of 5 times 10 to the power 4 newtons per coulomb at a distance 21 cm from its center. What is its surface charge density and its capacitance? So let's assume this is the sphere, and on the surface, because it is a conducting sphere, you have charges reside on them. Let's call the total amount of charge as Q coulomb, and we know the field it creates at a distance 21 cm, where the electric field here is 5 times 10 to the power 4 Newton per coulomb. We can use this data to determine this capital Q, and only after we determine capital Q we can determine the surface charge density. The field at that distance is given by the following equation: K Q over distance squared. So E is 5 times 10 to the power 4. K is the constant that we are familiar with, 9 times 10 to the power 9, times Q that we are looking for, over R squared. R is 21 cm. Let's turn that into meters, 0.21 meter squared. And Q can be determined. If you do the calculation, you get Q to be 2.45 times 10 to the power minus 7 coulomb. Having found the total charge, we can proceed to determine the surface charge density. Note that the sphere has a radius of 12 centimeters. So the surface charge density, let's call it sigma, is given by the total charge on the sphere divided by the surface area of that sphere, which is 4 pi radius squared. We know what Q is. It's 2.45 times 10 to the power minus 7 coulomb. Divide that by 4 pi. Radius is 12 cm. Turn that into meters, so 0.12 meter squared. And the answer will be in coulomb per meter squared. If you do the calculation, you will get the following value for sigma: 1.35 times 10 to the power minus 6 coulomb per meter squared. So that is the answer to part A. Now part B, the capacitance. This is a sphere, and you have plus charges on them. We shall take another sphere to be at infinity, and let's assume that sphere has sort of a negative charges on them. And the distance between them, the R, is large. So since we are trying to figure out the capacitance, capacitance is given by the charge on that capacitor over the potential difference between the plates. In this case, the positive plate is the sphere and the negative plate is the largest sphere, the large imaginary sphere, if you will. So delta V is V plus minus V minus. Now V plus is the potential on the surface of the sphere. It is just the charge on the sphere times that K over the radius of that sphere. Let's call it capital R. And V minus is potential there, which is at an infinite distance from that sphere. So that means it's 0. Putting all the information in there, so Q over that. So that means R over KQ. So that goes away. Your R is the radius of the sphere, which is 0.12 meter. K is 9 times 10 to the power 9. And that will give you the capacitance in the unit of farad. And then when you do the calculation, it will give you the following value. 1.33 times 10 to the power minus 11 farad. That solves the problem. Problem 2. A parallel plate capacitor is constructed by filling the space between the two square plates with blocks of 3 dielectric materials. The dielectric constants are K1, K2, and K3. These are the plates of the capacitor with length L. The separation of the plates is D. Assume L is much greater than D. Find an expression for the capacitance of the device in terms of the plate of area A, K1, K2, K3, and D, the plate separation. So let's do part A first. If you were to apply potential difference across the plates of this capacitor, then the electric field within the dielectrics would go that way. What that means is, it's as if you have two separate capacitors as far as K2 and K3 materials are concerned, and they are in series with each other. So let's do the 2-3 combination first. To combine two capacitors in series, we add their inverses. So the inverse of the net capacitance of 2 and 3 is 1 over the capacitance of 2 plus 1 over the capacitance of 3. We know the capacitance of 2 equals epsilon naught K2, the area of the plate that covers, so that is L over 2, and the other side of that plate is L, so that means is L squared over 2, and we divide that by the separation distance equivalent for that capacitor, D over 2, right there. Likewise, for C3, the capacitance for that part is epsilon naught K3 L squared over 2, because it has the same area coverage as K2, and to that we divide that distance, which is D over 2, for the plate separation. So taking the inverse of C2 and C3, we would get 1 over C23, or the inverse of the capacitance of the combination, to be D over epsilon naught L squared 1 over K2 plus 1 over K3. And C23 is therefore epsilon naught L squared over D K2 K3 over K2 plus K3. Next, let's bring in the K1 combination to get the overall capacitance. So C1 plus C23. C1, the capacitance due to that, is quite simply epsilon naught dielectric constant K1 times the area coverage of that capacitor, and that is just L squared over 2. because that distance is L over 2, and the other side of that plate is L, so multiplying both we get L squared over 2. The separation distance for that capacitor is just D. Now we have to add these two to get the overall capacitance, and that's going to be epsilon naught K1 L squared over 2D plus epsilon naught L squared over D times K2 K3 over K2 plus K3, which simplifies into epsilon naught L squared over D K1 over 2 plus K2 K3 over K2 plus K3. We note that since the original plate is a square plate with sides L, its area, A, is quite simply L squared. So we can rewrite the above result for C in a following manner. Epsilon naught A over D times K1 over 2 plus K2 K3 over K2 plus K3. And that is the expression that we are looking for. Part B, calculate the capacitance using the values A is 1 cm squared, D is 2 millimeters, K1 is 5, K2 is 5.5, and K3 is 2. Substituting these values in here, 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 and there, and taking epsilon naught to be 8.85 times 10 to the power minus 12 in SI units, we will get following number for C, namely 1.755 times 10 to the power minus 12 farad. And that solves the problem. As always, thank you for watching.